All right, so let's talk about graphing. So first off, function notation. So instead of necessarily, I mean, my screen just did something weird. Okay, it's back. All right. So we might sometimes write functions. Sometimes we might write it as like y equals x plus 2 squared plus 3. We could graph that, and it would be a parabola, and we could even say that the vertex is at the point -2, 3, and some other information. Not super important. But we could also write it as f of x equal to x plus 2 squared plus 3. And kind of the nice thing about this notation is you can kind of capture more information in one setting. What I mean is, like for this one, if I wrote y equal to x plus 2 squared plus 3, and if I want to know maybe what y was when x was equal to 1, I could say, all right, x equals 1, y equals 1 plus 2 squared plus 3, and I get y equal to 9 plus 3, which is 12. And to really know that the point is 1 comma 12, I have to write x and y. Whereas with this notation here, I can write the following. I can write that f of 1 equals 1 plus 2 squared plus 3, which is still 12. But this f of 1 equal to 12 tells me at the same time what x is and what y is. So it's just kind of nice notation. It says the point 1 comma 12 is a point on the graph. And so we often prefer this notation. We're definitely going to go back and forth. We're going to use both. We're going to use y equals the thing. We're going to use f of x or g of x or some letter of x equals the thing as well. So just try to get comfortable with using both types of notation because we're definitely going to do that today. And yeah, so let's graph some stuff. Mostly today we're going to talk, well, that's not true. We're going to talk about what people often call a lot of the parent functions, which are kind of like the original base graphs, and then how we can kind of manipulate them in a few different ways. So let's talk about the first one. We've already talked about lines and parabolas and circles. Now we're going to learn a few more graphs. So the first one is the square root graph. And so when I'm graphing this, there's a couple things I think about. I'm graphing, y equal to the square root of x, or if you prefer, f of x equal to the square root of x. And when I start to graph this one, I think about what my x and y values can be. So you could make a table, although eventually we're just going to graph this by just saying, well, it has this kind of shape. But I'm going to make a table of some nice values. For example, numbers that are easy to take the square root of, like 0. What's the square root of 0? It's 0. So I get the point 0, 0. And if I plug in 1, the square root of 1 is 1. So I get the point 1, 1. I could plug in 2. That point's harder for me to graph nicely. So I plug in 2, I get the square root of 2, which is an irrational number, right? It's not a nice integer. It's approximately 1.41, but I don't really want to try and graph that. So I'm going to skip it on my graph and just go to the next easy number, which is going to be 4. If I plug in 4 for x, the square root of 4 for y is 2. And we could go on. I could plug in 9, the square root of 9 is 3. And I think I went, let's see, 1, 2, oops. So I plotted this one wrong, right? This is at 1, 2, 3, 4, 5, 6, 7, 8, 9. I should have plotted this at x equals 4, y equals 2. and then x equals 9 and y equals 3. This is about what it looks like. Well, I should say these are some of the points on the graph. And then try and graph it so it looks nice. So we plotted a few points and then we connected the dots. So I should say, right, there's a lot of other points we didn't talk about, right? Like there's 2 comma the square root of 2. But there's really an infinite number of points, right? You can plug in any x value on the positive x-axis and get the corresponding square root value for the y value. You can plug in 3.1 and get this point here could be 3.1 comma the square root of 3.1. There are a few values we can't plug in for x for this particular function, right? We cannot plug in x equal to -4 because the square root of -4, although it is an imaginary number, we're not graphing imaginary numbers, right? This is equal to 2i if you want, but really we care that it's not real. So we can't graph that. We're only putting in things that give us real number outputs. The reason I mention that is because it has to do with the domain of this function. The domain, which is all the possible x values for the function here, is all the x's that are greater than or equal to 0. You could also write this in set notation as everything from 0 with a bracket to infinity with parentheses. The range in this particular function is actually the same. The range, though, is all the y values, and the y values also have to be greater than or equal to 0, which you could write as bracket 0 to infinity. So that's your square root function. And really, so I know I kind of talked about it in, is that 2 square root 3? This is that you talk about up here? On the
yes, that one.
Sorry, that is, so I was pointing out that you can pick any point, and yes, I realized I did not write it very nicely. That is the point 3.1, comma, the square root of 3.1. Just to point out that you can have kind of really any input that's non-negative, and there still would be some number, right? I don't know what the square root of 3.1 is. It's probably about 1.75. Sure, a bracket includes the point. So, right, 0 is definitely included in the domain because we can take the square root of 0. And in this case, infinity always gets a parentheses. Well, I should say in every case, infinity gets a parentheses because we never actually include infinity because it's not a real number. But there are some functions which we'll see more towards the end of class today where we will use the parentheses to exclude a specific value. All right. I will say when I'm graphing this, right? Whoops, I meant to erase all this beforehand. Oh no, I didn't. This is from. I was like, I didn't erase this thing. Yeah, this is what we talked about right there. Usually when I'm graphing the square root function, I do it much more quickly, and I think you should too. So if you're graphing the square root function, you're like, okay, I know I get 0, 0, and I know it kind of looks like this. And you can plot a point or two if you want. Like you could plot 1, 1. You could plot 4, 2. But really, my plot's not that good. And it doesn't have to be that good. It just has to be approximate. You can also, of course, graph things on Desmos. Desmos is useful. Let's see. Let me share here for 1 sec. All right, so here's the square root function. There's what it looks like. Not that impressive, really. It just kind of is. And it keeps, right? You can go out. And even though it doesn't look like it gets very big, it does get infinitely big. It just takes a long time to get really, really big. Okay, so let's move on to some more functions. Let's talk about the absolute value function. So, I'm going to graph y equal to the absolute value of x. Again, we could totally plot some points. In this case, x can be anything, right? In the previous example, x couldn't be negative. Here, it's okay for x to be negative. Because whether x, if x is 0, the absolute value of 0 is 0. If x is 1, the absolute value of 1 is 1. If x is 2, the opposite value, oops, opposite value was on the other side. And if x is positive, you're just getting x back. So we can start plotting things, say, okay, well, if I plug in a number, it's positive, I'm going to get back the same number. Same thing for 3, right? So it definitely looks like, at least on the right-hand side, I've got a line that looks just like whatever. That's why I usually graph it before I plot the points, because I sometimes miss. Right, I've got the point 1, 1, and 2, 2, and 3, 3, and 0, 0. But if I start plugging in negative values, negative 1, negative 2, negative 3, the absolute value of negative 1 is 1, and the absolute value of negative 2 is 2, and the absolute value of negative 3 is 3. So I get these kind of values to the left, the point negative 1, 1, and the point negative 2, 2, and the point negative 3, 3. So that's what my graph looks like. And we can also talk about the domain or range here. In this example, the domain is everything. So you can either say the domain is all real numbers. And I know we're talking mostly about substituting or plugging in integer numbers, but really, again, you could plug in any real number, meaning you could plug in 3.2 or negative 5.7 or positive square root of 8 or pi or anything. And all of those values, which are real numbers, give you something back. You could also write it as parentheses negative infinity, comma, infinity. All the real numbers between negative and positive infinity. The range here, on the other hand, again, the range is all the y values. The y values go as low as 0, but not any lower. So the y values go from, you could say y is greater than or equal to 0, or you could write it as bracket 0 to infinity. Zoom's trying to get me to update something. I'm like, no, I don't want to update right now. Okay. And then the third function we're going to work with mostly today is the cubic function. This is the one I'm never great at graphing. The absolute value function, like I could show you on Desmos, but the absolute value function is like super easy to graph, right? It's just this side looks like y equals x, and this side looks like y equals negative x. And that actually is what the absolute value function is. When x is positive, you get y equals x. When x is negative, you get y equals negative x, because the negative of the negative will make it positive. That one's easy to graph. I don't think I need to show you the graph on Desmos because like it's super straightforward. On the other hand, y equal to x cubed is something I am never really good at drawing. The typical points we plot are when x is negative 2, negative 1, 0, 1, and 2. And the corresponding y values are negative 2 cubed, which is negative 2 times negative 2 times negative 2, which is negative 8. Negative 1 cubed, which is negative 1. 0 cubed, which is 0. 1 cubed, which is 1. And 2 cubed, which is 8. So graphing this always feels a little dicey. So I have to go up to like 8. It is good to be able to graph things on your own without having to use Desmos. So I get the point negative 2, negative 8, and negative 1, 1, and 0, 0, and 1, 1, and 2, 8. And then we try and make it look nice. Kind of looks like that. That's not bad. Let me show you on Desmos, just because I do think it's worth looking at a nicer looking picture. Let me do this. So right here is the graph on Desmos. Y equals x cubed. You've got 0.00, got the point 1, 1, if you can click on it. It's weird. I wonder why some points let me like click and stay there, and other ones don't. But you also got the point 2, 8, and it goes on and on and on. And you can kind of see here if you zoom out, right? So again, it kind of looks like the y values are getting super big and the x values aren't getting very big. The y values are getting bigger faster, but the x values also keep getting larger and larger, right? There's no reason you can't let x be a bigger and bigger value, just like there's no reason why you can't let y be a bigger and bigger value. So here, for y equals x cubed, both the domain and the range are everything. So the domain is all real numbers or negative infinity to infinity, because the x values can go as far left and as far right as you want. Let me stop sharing here. And the range is also the same. The range is also negative infinity to infinity, because the y values go as negative and as positive as you could possibly imagine. So great. So those are three, what we usually call these parent functions: x cubed, the square root of x, and the absolute value of x, in addition to the parabola y equals x squared, which we've already talked about. These are parent functions that we often manipulate in various ways to get other kinds of graphs. So let's look at a few examples of these manipulations. And I'm gonna go back and forth between Desmos and drawing things, because I feel like, I mean, yes, I can draw these just fine. I can also show you on Desmos and stuff. So let's look at a couple things. First of all, let me share here. So the first question we want to answer is, what does a negative sign do? So if we look over here at y equal to, where'd you go? So let me turn you off. So here's y equal to x squared. And if we look at y equal to x squared, if we put a negative sign in front of it, flips it across the x-axis, right? So there's y equals x squared in green. There's y equals negative x squared in purple. On the other hand, if we instead put a negative on the inside of the function like this, it takes your, and now I know it doesn't look like it for an x squared function, but it takes your original function, y equals x squared in green, and it flips it across the y-axis, which in this case, since there's symmetry across the y-axis, doesn't look different at all. The same can be said, let's look at the square root function. So here's the square root function. If I do the square root of negative x, so if the negative is on the inside of the function, it's going to flip it across the y-axis, like that. On the other hand, turn both those off. If the negative is in front of the function, or outside of the function, as I usually say, it flips it across the x-axis. So again, here's the original function, y equals square root of x. And then here's the flip, y equal to negative square root of x. So here's what I really want to say. I want to stop sharing to write some stuff down. So if our function is y equals f of x, then here's what happens. Y equal to negative f of x flips the original function across the x-axis. And I say flip, the more mathematical term is reflects. So this negative outside reflects the original across the x-axis. On the other hand, if you have y equal to f of negative x, where the negative is inside the function, right? I have you put in the negative on x before you do anything else. This is going to reflect across the y-axis. And again, our examples were, so the original was y equals x squared, and y equals the absolute value of x. Sorry, I did the square root of x, not the absolute value of x. So this function, y equal to negative x squared, looks like this, right? It's the regular x squared function, but flipped over the x-axis. Or y equal to the square root of x, if I do the negative on the x before I take the square root, I'm going to flip that across the y-axis. So it's going to look like that instead of like the original. Let's look at a couple more examples. Well, in fact, here's an example that's not all that good. So if you look at this function, so it might not be obvious, I don't know, but we can kind of see that whether you reflect this across the x-axis or across the y-axis, both of those reflections are actually going to look the same. So to reflect across the x-axis, we would do a negative in front of the function, which would mean we would have y equal to negative x cubed, which is just negative x cubed, which I'll graph in a second. To reflect across the y-axis, my spelling is really good. Reflect across the y-axis, we would get y equal to negative x quantity cubed. But a negative number cubed is a negative times a negative times a negative, which is still negative. So this is negative x times negative x times negative x, which is negative x cubed. And these are the same. So whether you reflect it across the x-axis or across the y-axis, you're going to get the same result. And it's going to look like this. Except not as ugly as that. So yeah, so there's another example of, okay, reflections. Well, there's an example of reflecting, but I want to do one more example that actually looks different. Two more examples, actually. So I look at the graph of f of x equal to the absolute value of x, which we know looks like this. People usually think of it as looking like a V shape. Then if I do y equal to negative f of x, which is the negative of the absolute value of x, that's going to take that and give me negative y values, right? Here, if I plug in the next number, I'm going to get positive outputs, right? Whatever x is, the absolute value is going to give me some non-negative number. Here, if I put in the next number, I'm going to get something positive for the absolute value, but then we get the negative of that. So all my y values are the opposite sign than they were. So I took that graph and we flipped it across the x-axis by putting a negative sign in front of the function. So negative in front of the function flips across the x-axis. Negative on the x inside the function flips across the y-axis. Let's talk about adding and subtracting a number. So what does adding a number do to the graph? Well, it depends on where you add it. So let me show you some examples. So let's unclip this one for a second. So here's the square root function again. Great, looking normal, just like it is. If we add, 4 on the outside, right? So I see this is definitely adding 4 outside. I'm sorry, of the function. It's going to shift it up by 4. So, and that makes some sense because here, right, we're plugging in 0, square root of 0 is 0. Here we're plugging in 0 and the square root of 0 is 0, but then we're adding 4 to it. So we're getting a y value that's 4 bigger. And right, all the points are exactly 4 larger. So this is the 0.11, There's the 0.15 approximately. On the other hand, if we add on the inside of the function, it actually shifts it to the left, right? So here I get the point 0, 0. Here I get the point -1, 0, because x had to be 1 less than it was before to get the same corresponding y value. And I find personally that adding or subtracting on the inside is always a little counterintuitive. Let's do some more examples. Whoa. So for f of x, we have two things. The screen keeps doing something bizarre. Sorry, that's a serious problem. For f of x, we have y equal to f of x plus c, where we add on the outside, shifts the graph up c units. Oh, sorry, I used d in the no, sorry. F of x plus d shifts the graph up d units. So if d is positive, it's going to shift it up. If d is negative, it's going to shift it down. On the other hand, y equal to f of x plus c is going to shift the graph horizontally. This is where I feel like things are a little bit weirder, right? It's going to shift it left if c is positive and right if c is negative. And I'll tell you how I think about this in just a second. Sorry, I kind of meant to write that here too. So you go up if d is positive, down if d is negative. So here's the idea. And I really like the square root function for this. I want to graph y equal to the square root of x minus 2. I know from what I just said, that's going to shift the original parent graph down by 2 units. But I can also look at the table and say, okay, we got x. I'm also going to look at the square root of x and then the square root of x minus 2, which is my y. So I'm going to pick the usual suspect values for x's, meaning the nice, easy things to take square roots of, like 0, 1, 4, and 9. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. And then if I do the square root of x minus 2, I'm just taking all those values and subtracting 2 from them. So my y values are all going to decrease by 2 while the x values remain the same. So 0 minus 2 is negative 2. 1 minus 2 is negative 1. 2 minus 2 is 0. 3 minus 2 is 1. So I'm taking all those original y values and just moving them all down 2. Well, that exactly corresponds to a shift of down by 2. So I get the point 0, negative 2, 1, negative 1, 4, 0, and sorry, my line there is not straight at all. It's annoying. Right, that's what's so nice about this. Most is all the lines are straight. Unlike my graphs where the lines are not. So, and then we get 9, 1 way over here. So look kind of like that. So here's the way I think about it. When you add or subtract on the outside of the function, the x's you use to find your nice points still stay the same, and the y's you get increase or decrease by however much you add or subtracted by. Now the thing is, the opposite kind of thing happens when you add or subtract inside the function. Let's look at something like y equal to the square root of x minus 3. So here's the way I kind of think about this. Usually, if I was trying to graph the square root of something. So I'm making my table. Here's the deal. Usually the things I want to input into the square root that are nice are the same values I just talked about on the other side of the board. 0, 1, 4, 9, 16, right? All the square numbers. So I want x minus 3 to be 0, 1, 4, 9, 16, etc. Because I know that if x minus 3 is 0, the square root of 0 is 0. And if x minus 3 is 1, the square root of 1 is 1. If x minus 3 is 4, the square root of 4 is 2, and so on. But here's the thing, that's what x minus 3 has to be, but I'm not graphing x minus 3 on the x-axis, I'm graphing x on the x-axis and y on the y-axis. So I need to know the actual x values. So I'm going to say, well, if I want x, and I know what x minus 3 is, I'm just going to add 3. So if x minus 3 is 0, then x has to be 0 plus 3. And if x minus 3 is 1, x has to be 4. If x minus 3 is 4, x has to be 7, 12, and 19. So the way I kind of think about it is this way. To get the same y values I normally would want, when I'm taking the square root of x minus 3, x has to be 3 larger than it would have been normally, right? Normally, if I was doing, the square root of x, I would say, oh, x is 0, y is 0, x is 1, y is 1, etc. But now, to get the same y values, x has to be 3 larger than 0 to get 0, because 3 minus 3 is 0, and the square root of 0 is 0. X has to be 3 larger than 1 to get out the same 1, right? X is 4, 4 minus 3 is 1, the square root of 1 is 1. X has to be 3 larger than 4 to get 2, because 7 minus 3 is 4, square root of 4 is 2. So that's how I think about when you subtract on the inside, if you're subtracting, doing x minus 3, x has to be 3 larger than it was before to account for the 3 you're subtracting, which is going to end up shifting it all to the right because x has to be bigger, further right than it was. So I started at the point 3, 0, I get the point 4, 1, and it just keeps going like that. And then we can put a couple shifts together, a vertical and a horizontal. So for example, we could say, all right, I want to graph f of x equal to the square root of x plus 1 plus 4. The plus 1 inside is going to shift it 1 to the left. The plus 4 outside is going to shift it 4 up. And I'm going to think about what happens to my endpoint for the square root. The square function usually starts at 0, 0, and then does this kind of thing, right? There's my usual y equal to the square root of x. But now I'm moving that point at 0, 0, I'm moving it 1 to the left and 4 up. So I'm like, oh, here's my starting point at -1, 4. And then I'm going to just keep going like this. So it's going to do that. I'm going to run out of room because I have pi. That's the idea, right? All of these points are 1 to the left and 4 up from all those points. And then we might have enough room. Sure, we can fit something else on here. We can do the same sort of thing with like f of x equal to, what have we got here? The opposite value of x minus 2 minus 3. This is going to take your usual absolute value function and shift it 2 to the right because x has to be 2 bigger than it was to get the same y values, and then 3 down. So normally the absolute value function would have a vertex at the point 0, 0, right at the bottom of the V. But I'm going to move that bottom of the V 2 to the right and 3 down. It's right there. And 2, -3. Right, when x is 2, y or f of x is 0 minus 3, which is -3. And then we know it looks like the usual line to the left and line to the right. We can certainly find these intercepts. Well, that's not really the point right now. we can also combine flips or reflections with shifts left and right. So for example, we could do, say, the graph of the square root of negative x plus 3. And usually I kind of work from the inside out. So I'm going to do all the horizontal stuff first and then the vertical stuff after. That's something else I should say. The stuff that happens inside the function, like the negative inside or the adding inside, affects the function horizontally. If you get a negative on x inside the function, you do a horizontal flip across the y-axis. If you add or subtract inside the function, you get a horizontal shift. On the other hand, for the negative outside the function, you get a vertical flip across the x-axis. If you add or subtract outside the function, you get a vertical shift. So I want to emphasize that a lot. If you do things inside the function, you affect it horizontally. If you do things outside the function, you affect it vertically. So this one's going to have a horizontal reflection across the y-axis. And then we're going to add 3. So normally, we would start with this. Right, there's your y equal to the square root of x. And then we're going to flip it. So it's going to look like that. There's y equal to the square root of negative x. And then I'm going to add 3. Again, I didn't really give myself enough room. Move this over here. So then I'm going to be like looking like this. Just looking like this function, but moved up 3. So that's kind of how I think about the process of doing a reflection and a shift. Is first I'm kind of working with the inside stuff, then the outside stuff. Let me look at more. Sure, let's look at y equal to negative absolute value of x plus 1 minus 3. And I'm going to kind of work, again, basically I'm kind of starting as close to x as I can and then seeing all the pieces that kind of affect it as they go along. So first I'm shifting it 1 to the left. Then I'm flipping it vertically because the negative is on the outside of the function. And then I'm subtracting 3 or shifting down by 3. So I'm taking my original absolute value function, which looks like this. I am shifting it 1 to the left. So 1 left. Then I'm flipping it vertically or reflecting it vertically. So instead of opening up like this at the point negative 1, 0 as its vertex, now the vertex is at negative 1, 0 still, but it's going like that. And then I'm going to move it down 3. So it's going to look like my vertex now is going to be negative 1, negative 3. And it's going to be a V opening downwards, like that. Kind of funky. So the order that you do things in, if you have shifts and or reflections, is first you do a horizontal shift, then you do a horizontal flip, then you do a vertical flip, then you do a vertical shift. And that's, to me, that's always the order. Some people like to do things slightly differently, but I feel like it always works best if we do that. If you look at the notes, I think there's actually something that someone wrote about it that's not quite correct. It kind of depends. They wrote that you should do any flipping before you do any shifting. And while that's not wrong, I think it's easier to do all your horizontal things before you do any of your vertical things. So for example, if I wanted to graph, say, f of x equal to, what have I got here? The, sure, the negative square root of negative x plus 2 plus 3. It's got all the things. It's got every kind of flip, every kind of shift. So I'm going to first, and this is where we have to be super careful, I'm adding 2, so I'm going to shift left 2. Then I'm going to do a horizontal flip. Then I'm going to do a vertical flip. Then I'm going to shift it up 3. I should say left 2. Now watch this, because it can be a little bit tricky. So first we're taking the square root function and going left 2. So it looks kind of like that. Then I'm going to do the horizontal flip. So I'm going to flip it around the y-axis. So this point here at negative 2, 0 is going to come be over here at positive 2, 0. So it's going to look like this. And then we're going to do a vertical flip, so flip it over this way. This is a horizontal flip. I have to erase this left 2 here. So then a horizontal flip is going to, then a vertical flip is going to flip it over this way. So like that. And finally, we're going to shift it up 3. So this point that's starting at negative 2, 0 is going to move up 3 to be at 2, 3. And then it's going to come down this way. Eventually it's going to cross the x-axis way over here. You could totally find the domain and range of this function. The domain is everything from negative infinity to 2. Bracket 2. Right? X can't be bigger than 2, because if x was bigger than 2, then you'd have a negative inside the square root. And the range, if we look at the graph, the y values go all the way down to negative infinity and all the way up to positive 3. Okay, there's 2 parent functions left I want to talk about. They're pretty short and sweet. I would also, what I would really say about all this flipping and shifting stuff is, I think if you play around with it on Desmos just a little bit, like take a function, any parent function like x squared or x cubed or square root of x or absolute value of x, and just try adding on the inside or adding on the outside or putting a negative on the inside or the outside, I think you might get a good feel of how things work pretty quickly. Let's look at these last couple functions. The last 2 functions I'll look at are, the first one is f of x equal to 1 over x, which is called the reciprocal function. You're taking the reciprocal of x. So we could plot some values. What's the only thing x can't be? What am I not allowed to divide by? Yeah, exactly. So x can't be 0, which means 0 is not in the domain. So the domain here is everything from negative infinity to 0, parentheses, since we don't want to include 0. And then a u for union, everything from 0 to infinity. And we'll see when we graph it in just a sec that the range is actually the same. So we could plug in some values for x like 1 or 2 or 3, and the y values are going to be 1 over 1, 1 over 2, 1 over 3. So as x gets larger, y gets smaller. And the same thing if x is negative. If x is negative 1, negative 2, negative 3, the y values are correspondingly negatively smaller. Negative 1, negative 1/2, negative 1/3. So the graph of this, we plot a few points. If x is 1, you get 1. If x is 2, you get 1/2, and so on. If x is 1/2, 1 over 1/2 is 1 times 2, which is 2. So here's what we see. As the x values get larger, the y values get smaller. As the x values get smaller, the y values get larger. So we have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And it's also true on this side, except everything's negative. So we have a horizontal asymptote at y equal to 0. We have a vertical asymptote at x equal to 0. And the range is also the same as the domain here, right? Because you can get any y value except for 0, because 1 over x will never equal 0. Okay. And then the the other function that's similar to this, but a little bit different. Is the function y equal to 1 over x squared. How do you get the asymptotes? So horizontal asymptote is a value that the function gets closer and closer to as x gets larger and larger. So here, as x gets larger, the y values get smaller and smaller. So the horizontal asymptote is 0. The vertical asymptote comes from when the expression gets really, really large. So as x gets closer and closer to 0, right? If x was 1/2, you get 2. If x is 1/3, 1 over 1/3 is 3. If x is 1/1000th, which is still positive but really, really small, the y value is 1,000. So as x gets really, really, really close to 0, the y values get infinitely large. And the same thing is true on this side, except that they are negatively infinitely large. Right? So x gets really, really close to 0, but negative y is really, really negatively large. You can also just look at the expression here and say, oh, if you're dividing by 0, that's going to be where you have a vertical asymptote. And so in a similar way, we're going to see that this function also has a vertical asymptote at x equals 0. Because as x gets very, very close to 0, the y values are going to get huge. And that's something that's generally true. If you have a fraction, if the denominator gets small, the whole thing gets big. If the denominator gets big, the whole thing gets small. So you have a vertical asymptote at x equals 0, you have a horizontal asymptote at y equals 0. And the graph looks similar to the previous one, except for a couple things. One, so you still have the point 1, 1. If x was 2, then you'd have the point 2, 1/4. So it's going to get smaller faster, right? On the previous one, we had 2, 1/2, and we have 2, 1/4. So it gets small very fast. Like that. The other thing that's a little different is both sides are positive, right? If you have 1 over x squared, it doesn't matter if x is positive or negative, the y values are always going to be positive. So on the left-hand side, it's going to look like this. So you have a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. The domain is still the same as before. It's everything from except for 0. The range, on the other hand, is only positive values. Everything from 0 exclusive to infinity. So those are some graphs, some parent graphs. I mean, again, I would really say, like, I would really encourage you all. I know we're out of time, but I just want to say this last thing here. I would really encourage you all to play around with Desmos, right? Like, you can do all sorts of things. You can kind of see, right? If I, for example, I take this function here, right? I added 1 inside, which shifted it left 1 and added 4. But then I could put like a negative in front of it. And you can see how, oh, right, I added 1, so I shifted it left. I flipped it over. So in fact, let me get rid of that. Right, I added 1, shifted left, flipped it over vertically. And then after flipping it over vertically, I shifted it vertically up 4. So I really, really think it would be good for you to try out some things with Desmos, because I think you can really, I mean, right, because graphing, can be kind of time consuming. You're like, I have to graph the thing and see where it goes. But here you can just kind of see the graphs right away. So if you want to really get a good idea for how things look, play around with this stuff and kind of see what you get. For example, another example here, if you take y equals x squared, well, let's say, let me turn it on. Right, I can then say, well, what if I subtract 3 on the inside? So put some parentheses around that. And then if I subtract 3, oh yeah, it moves it 3 to the right. If I add 2, move it 2 to the left. What if I put a negative on x? Oh, wait, that's weird. If I put a negative on x, it doesn't really do anything. So then if I add 2, okay, well, it still shifts it 2 to the right. Oh, that's weird. Well, that's because right, it really shifted it 2 to the left because I added 2 and then it flipped it horizontally, right? 2 to the left, flipped horizontally. Or then we can say, well, what if instead I shift it to the left and then put a negative on the outside? Oh, that flips it over. And then what if I, add 3 out here? Oh, that shifted up. Oh, what if I subtract 3? Oh, that moves it down, right? So I think this is a useful tool to kind of mess around with things.